Hey, hello guys, welcome, vandanam, namaskaram. Today we are going to see complete one-shot video of solutions. So already we have seen about, I don't know how many parts we have already seen, but we have seen some parts. Okay, where I've explained about colligative properties. In colligative properties, till freezing point, okay, a depression and freezing point, and elevation and boiling point. Okay, so till this much level we have seen. Today we are going to see complete one-shot video along with abnormal molar mass, along with normal molar mass. All those are there in our concepts, right? So everything we are going to cover one by one. First is solution. So we will start from the basics and we will go. Okay, so first is solutions. What is a solution? Solution is actually a homogeneous mixture of two or more than two substances. Okay, here the word substances mean it can be like either solute or it can be solvent. So that means when you add a solvent along with a solute, you will be getting a solution. That's it. Okay, so what is a solvent and what is a solute? Solute is the substance that is being dissolved in a substance. Okay, that means, for an example, when you are having something, okay, so when you are having water, okay, you take it as water. So this is H2O. Okay, so to this I'm going to add sugar. So here sugar will be generally what? Okay, sugar is the thing that is being dissolved in H2O. You will not say that H2O is the thing that is being dissolved in sugar. Okay, so first you are having what? First you are having H2O, then second you will be having sugar. Yes, right? And sugar is what being dissolved in H2O. So being dissolved. And H2O is the thing that dissolves. That dissolves sugar. Yes, right? So H2O is the thing that dissolves sugar, and sugar is the thing that is being dissolved in H2O. In H2O. So here, which is being dissolved, that is known as solute. And the thing that is dissolving, okay, the thing that is dissolving is what known as solvent. Okay, and you can see generally solvent will be more in quantity. Okay, so this one quantity will be high, and this one's quantity will be generally less. It's not generally, it will be less only. You can just see when you are adding sugar to water, you can know that you will know that sugar will be always less in quantity than water comparatively. Okay, you cannot add like 10 kgs of sugar and you cannot just put 2 droplets of water. It won't be correct. Okay, then the sugar will be converted into sugar, not sugar syrup. It will be converted into, I don't know what will be converted, but it will be a brown color liquid. Okay, it is generally used caramelized water. Okay, caramelized milk or caramel. Yeah, it is caramel syrup. Okay, so that is what basic. When you are adding this and this, you will be getting solution. And solution is actually of 3 different types: binary solution, ternary solution, and quaternary solution. Well, coming to here, binary. The word binary, bi means 2, ternary. Okay, normally it is tri, but we cannot write trinary, so it is actually ternary, and here it is quaternary. So here ter means 3, quat means 4, and bi means 2, as I said already. Here you can see that there are 2 different components in a solution. Okay, 2 different components in a solution. That is what binary solution means. So that means what? One is going to be solute and another is going to be solvent. It is mandatory. Okay, many solution that we are going to discuss is going to be my binary solution. Okay, many solutions that we are going to discuss is binary solution only. Then coming to the case of ternary solution, it will be having 3 components in it. That means it will be having one solvent, and then 2 solutes. Okay, coming to quaternary solution, it will be also having one solvent only, but instead of having two solutes, it will be having three solutes. Okay, you will be having three solutes. So you have to note that in binary, in ternary, in quaternary, in pentanary, in hexanary, like that will be going on. So in all these solutions, in all these types of solutions, the number of solvent is going to be one only. Okay, only the solute is going to change. Okay, the number of solute is what going to be changed, but this will be lying constant. Okay, so next is one classical condition is here, that is when solvent is water. When you are having a solvent which is water, then that particular solution is said to be aqueous solution. Okay, so the word aqueous means actually water in Greek, I think. Okay, we have seen aquaman, we have seen aquarium, all these, right? Because aqua means water. So when you are having water as your solvent, then it is going to be aqueous solution. Okay, here I have written types of solutions. Okay, so generally, in general, you are going to deal with three different types of solutions. First is solid solutions, liquid solutions, and gaseous solutions. Well, here it is also a classification of solution, but it is based on number of components. Okay, here it is based on their states. Okay, actually there are a lot of states in our world. Okay, now in this universe there are lots of states, but very well known are three only. What are those three? Solid, liquid, and gas. But other than this, or also there like Bose-Einstein condensation is there, plasma is there, then even yeah, a lot of things are there. I studied a lot, but I forgot. It's not coming out. Okay. So here what you have to see is one point that I have to say before going here is you have to take the substances which are listed here in their respective room temperature only. Okay, so as I said that solute, okay, solute is the thing that is going to be dissolved in solvent. So solute will be less in amount. Okay, so solute is going to be less in amount and solvent is going to be more in amount. Okay, so come here. First is solid solutions. Here solid solution means that solvent is going to be solid. Okay, and also one more thing that I have to say, if solvent, okay, is solid now, then solution is also going to be solid. If solvent is liquid now, then solution is also going to be liquid. If solvent is gas, then in that case solution is also going to be gaseous state only. So solvent is the substance that decides whether a solution is liquid or solid or gaseous in state. Okay, so that means in solid solutions every solvent is going to be in solid in state only. Only the solute is going to be in different types of states. Okay, so first is you are going to deal with solid and solid, where both solvent and solute are solid in state. So best example are ornaments. Okay, gold ornaments, where they will be adding gold, and along with that you will be also having copper, which is an alloy. Okay, gold ornaments are a type of alloy. In F&D block elements applications we will be studying about it. Okay, so next is you will be also having coming to next case, which is, I will just zoom it. Okay, so then the next thing is going to be where here, in this case where solvent is always solid. Okay, in solid solution solvent is always solid, where now we are going to deal with when liquid is solid. Okay, in the time what you have to see is you have to see amalgam. Okay, amalgam is the example where you will be taking a small amount of mercury and you will be adding metal, okay, impure metal to it in order to metallurgify it. That means in order to separate impurities and purities from it, and that is what actually metallurgical process is, which we have studied in our class 10th standard. Okay, next is when you are having gas. Okay, when you are having gaseous state as solute. Okay, so best example is going to be hydrogenation. Okay, so you will be having ethene and ethyne. In hydrocarbons of class 11th standard we have studied that when you are adding hydrogen, okay, when you are adding hydrogen in presence of palladium, where palladium is the catalyst. Okay, so what is a catalyst? Catalyst is which reduces the ionization, not ionization enthalpy, the initial amount of energy that is required in order to convert reactants into products. Okay, so EA, it is that energy is said to be EA. okay, yeah, that energy. This energy will be high for slow reactions and this energy will be less for fast reactions. So this catalyst will be reducing it. In catalyst itself, we are having totally 5 different types: positive catalyst, negative catalyst, catalytic poison you have, promoter you are having, auto catalyst you are having. Very good example is actually for Habeas process I can give you. Okay, but that one will be dealing everything we will say in chemical kinetics. Okay, here we will discuss only about solutions. Okay, so this one. Then when you are dealing with liquid solutions, so liquid solutions in sense solvent is going to be liquid and your solute is what going to be in different states. Okay, so first is solid and liquid. Okay, sorry, liquid and solid. That means solvent is liquid. Okay, solvent is liquid and then your solute is what? Solid in state. So best example is actually going to be what? Your lemon juice is an example. Your lemon juice is an example. More than that, not lemon juice. Okay, so lemon juice is where liquid. Lemon juice is where liquid. I can give you where your sugar syrup is an example. Okay, in gulab jamun and in rasagulla we are having, right? Well, in rasagulla milk is what is there. No, water is also there, but gulab jamun will take. Okay, gulab jamun syrup is there, right? The sugar syrup. So that one is there, and here I've given you the formula of sugar, which is C12H22O11. Okay, next is when your solvent is liquid. Okay, we are dealing with solvent is liquid and your solute is also liquid. So in that time both are liquid only. So here only I can give you your lemon juice, your orange juice, and very common example, that is alcohol. Okay, so alcohol is being diluted with water, but the trend has got changed. Nowadays they are diluting water with alcohol only. Okay, so next concept is the same. So liquid is actually your solvent, solute or solvent. Oh, it's confusing for me. Solvent. Okay, so liquid is solvent and then your gas is solute. So that means what are carbonated drinks. Okay, Pepsi, Miranda, Coca-Cola, very fancy drinks. Okay, so that will be coming under this category. Now we have entered into the phase of gaseous solutions. So where your solvent is going to be gas here and your solute is going to be solid liquid gas. So when it is solid, the best example is actually the camphor. See, in the process of sublimation of our class 8th standard, we have studied it. Yes, right? So camphor is a sublimable substance where the sublimation kit is there, right? I have that kit. That is why you can remember that sublimation process of class 8. I did that experiment. You have to take that camphor and you have to heat it and it will be directly converted into solid small particle. Okay, it will be just directly converted into, it is actually gaseous state only, but the solid particles will be like this much big solid particle is there now. If this much is there now, then it, while because of heat, all the bonds will be broken down and then it will be like this. Okay, so this is actually considered as gas, but actually in reality, in truth, okay, it is going to be solid only. And another example is actually nitrogen plus camphor. Actually our atmosphere is completely filled with what? It is completely filled with, not completely, the major part is taken by nitrogen only, right? So that is why we have written here nitrogen. Next is same here, when your solute is going to be liquid. Okay, so in this case your example is going to be chloroform plus nitrogen. I don't remember anything that we have studied in our previous standards. If we have studied, you can comment in the comment section. Next is going to be both are gaseous in state. Okay, well, this example is kind of important and very easy example. This is actually air, and this solution, okay, this solution is also known as true solution. Air is also known as true solution. Okay, I know I do not explain this that well. I'm not satisfied with it. But anyways, okay. Now, next thing is you are having types of solutions based on their concentration. Okay, so first is you are having unsaturated solution, then you are having saturated solution, at last you are having supersaturated solution. Well, what is now coming to saturated solution? saturated, then unsaturated, then supersaturated. See, here saturated solution, first we will come with unsaturated solution, okay? In case of unsaturated solutions, it means that you are having a liquid, okay? You are having a liquid, okay? So this has liquid net. Okay, imagine that this is actually water. Okay, so you are having around 50 ml of water inside this particular beaker or inside this particular vessel. Now, this water is having the ability, this water is having, okay, let us take, it has 500 ml of, okay, water. Let us take, it has 500 ml of water, and this has the ability to dissolve about 50 grams, or let me take 500 grams itself, okay, 500 grams of sugar, okay, 500 grams of sugar. So see, this is actually water, right? Water, H2O molecule is there, that means it is going to be like this, 104.5 degrees is what their bond angle is, okay. Well, that's something in our class 11th and itself we have studied, right? So you are having this one. When you are having more water molecules like this itself, there will be automatically some space that will be created between two molecules. So that is known as intermolecular space. Okay, intermolecular space. Inside the space is where these sugar molecules are going to be deposited. Okay, when you are dissolving them, automatically those sugar particles or those sugar molecules will be broken down, and then they will be situated between this small space only. Then actually this is what is happening. So that is why, since this 500 ml of water is having enough space to accommodate 500 grams of sugar, okay, to accommodate 500 grams of sugar, okay. So that means when, okay, in case I'm increasing heat, okay, now I've started to give temperature. So if temperature is being given, then automatically heat will increase, right? Okay, then if heat is being given, then kinetic energy will be increased. Yes, right? If kinetic energy is being increased, then also the momentum will be increased, then the velocity will be increased, automatically the volume will be also increased. Okay, automatically the volume will be also increased between these two. That means the space between these two water molecules will be amplified. That means it will be more. Okay, comparatively it will be more. So now, if this is what the space in the beginning, then later it will be, okay. So then later it is going to be like this. Okay, a big space. Big space. So that means what? Now space has become bigger. Okay, so that means you can accommodate, naturally this water can, okay, naturally 500 ml of water can accommodate only 500 grams of sugar, but since the space has got amplified, that means this, now in this condition, and then now in this temperature, it can accommodate more than, okay, it can accommodate more than 500 grams. Okay, and also now for an example, it can accommodate, okay, now for an example, this 500 ml of water can accommodate in high temperature, okay, in high temperature can accommodate approximately, we can take 700 grams, okay, 700 grams, okay, 700 grams of sugar. So in high temperature, now what I've done is I've stopped giving heat. So temperature will not be increased, heat will not be increased, kinetic energy will not be increased, everything will come back to its own normal position. Everything will come back to its own normal position. That means the space, okay, the space which has got bit, okay, the space which has got more, okay, larger, that will be retarded. The space, the distance between two molecules, okay, two water molecules will be retarded, then automatically the sugar molecules which has got deposited at high temperature will be again coming out of the water. That means they all will be suspended in the water. Now in this particular time, instead of saying it as a solution when it is being suspended, right, that means it is not completely dissolved. So now what you have to say is, you have to say it as a sol. Okay, what you have to say is sol. See, solution, there are totally three different things. Solution you are having, okay, so solution you are having, then you are having sol, then one more thing that is actually known as suspension. I think once I will check. Yeah, suspension will be correct. Suspension. Suspension. Well, see, this is not good. That means I'm going to erase it. That is why I'm writing like with this much of awful handwriting. Solution means the solute has 100% got dissolved in the solution. So in the solvent, the solute has 100% got dissolved. But here it has not got 100% dissolved. Okay, that means some percentage is remaining. Here, very less percentage is what has got dissolved. Okay, so that is what suspension is. Actually, suspension means nothing has got dissolved at all. For the best example is sand in a water. Okay, decomposition and non-decomposition, sedimentation will be happening. Okay, so sedimentation will be happening in case of suspension. Okay, so coming back to here itself. Okay, so first case. Okay, first what I'm. Okay, so I hope you can remember all these concepts. Now, since there is 500 ml of water, first case what I've done is I've added, okay, so 300 grams of sugar in the first case. Okay, that means this water can still accommodate 200 grams of sugar, right? So that means it can still dissolve. So since it has still the hunger to dissolve, it has not yet completely satisfied its limit. Okay, still it has some more thing that can be dissolved. So that means here it is unsaturated. In this condition, okay, it is unsaturated. But when you are actually accurately, when you are adding 500 grams of sugar, okay, when you are adding 500 grams of sugar, then it is going to be saturated. Okay, then it is going to be saturated. When you increase, okay, when you increase heat, so now heat has got increased, the distance has got increased, and also the amount of accommodating sugar level has also got increased. So now it has got 700 grams. So that means now, for an example, you are adding to here 650 grams. Okay, 650 grams. Now also it is unsaturated 1P. Okay, now also it is what? It is unsaturated. Sorry, it is supersaturated. Okay, now it has got supersaturated. So as you reduce the temperature, here is the fun fact. Okay, this process is done wantedly by many people in order to crystallize. Okay, this supersaturated thing is there, right? It is done for crystallization. Okay, crystallization, blah blah. Okay, so crystallization it is done so that you can get the purest form of that thing. See, when you are having NaCl, right? You just do this in your home, and what you have to do is you have to keep a thread in there. Then let it to set. Okay, then after that you can see that around the thread completely salt will be there. That salt is the purest form of salt. Okay, because there won't be any impurities in that. That is what I've studied in my class 9th standard of crystallization process, where you'll be using this one. Okay, so that's it. Okay, unsaturated, saturated, supersaturated. Now we'll be seeing about definitions. Okay, so when you are having unsaturated solution, more solute can be dissolved at room temperature. That means what did I say here? Okay, what did I say here? See, that means here only 300 grams of sugar has been deposited. That means that much is what the amount that has got dissolved here. So still 200 grams can be deposited, not deposited, still 200 grams can be dissolved. So that means still more amount of solute. So here, what is there? Sugar is the solute, right? So that means more amount of solute can be dissolved at room temperature, at standard temperature. Then next is we are going to see saturated solution, where no more solute can be dissolved, because in saturated solution it has got reached to its maximum peak point, which is 500 grams of sugar. More than this, there is no way it can happen. Okay, so that means it has got to its absolute maximum amount of what is that? Dissolution. Yeah, dissolution. Next is this is at room temperature. Both unsaturated and saturated you have to discuss only at room temperature, whereas supersaturated, this alone you are not supposed to discuss at room temperature. You have to discuss at some higher temperature than the room temperature. So that means a solution which is formed by adding maximum amount of solute, okay, at room temperature. This is what it means. Okay, next is methods to calculate concentration terms. Okay, so methods to calculate concentration terms. Here, when you check here, I have got still more formulas than I have written here. I will say one by one. First is mass percentage. Okay, now I don't want spectacles. I will do this one later. Okay, so first is mass percentage, which is mass of the solute divided by mass of the solvent. Not only here, everywhere, whenever you get the word as percentage, what you have to remember is, you have to remember that it should be always solute by solution. Okay, solute by solution with respect to its particular prefix. So here if it is mass percentage, it should be mass of the solute divided by mass of the solution into 100, because here percentage is there. Percentage now it is into 100. Then volume percentage in sense mass of solute, volume of solute divided by volume of solution into 100. Okay, then when you are having mass by volume percentage, it should be mass of solute divided by volume of solution into 100, since percentage is there. Okay, next you are having parts per million is there, parts per billion is there, parts per trillion is there. So in case of parts per million, it is just number of parts of one component divided by total number of components. Okay, generally this is what the formula that they have given, but you can use this formula. Okay, this formula is where you can very easily use, that is mass of solute divided by mass of solution into 10 to the power of 6. Okay, so million now what? Million means 10 to the power of 6. Billion now 10 to the power of 9. Trillion now 10 to the power of 12. Quadrillion now 10 to the power of 15. Like that will be going on. Okay. Here parts per million is actually mass of solute divided by mass of solution, like that also you can see, because here that one component, number of parts of one component divided by total number of components is there, right? See, this parts per million, okay, PPT, then parts per billion, then parts per million, okay, parts per trillion, parts per billion, parts per million. All these will be used when the solute, okay, when the solute is extremely less and solvent is extremely high comparatively with solute. Okay, is extremely high. Okay, that means what? For an example, what example can I take? We will take about 10,000 liters. Okay, 10,000 liters. Okay, so in this 10,000 liters, there will be many molecules. Yes, right. What liters? Liters of H2O. Okay, in this 10,000 liters of water, there will be many molecules. Okay, so what I've done is I have taken a drop of what is that? Chlorine. Okay, a drop of chlorine, one drop. One drop of chlorine is what I have taken. So I have put that one drop in water. That means what? In this large amount of water, only one drop of chlorine I have put. Okay, only one drop of chlorine I have put. So that means in this many part, okay, this is actually many part and this is just one part. Comparatively, when you are comparing this is actually going to be, this one drop is what? One part, and this is going to be millions and millions and millions of part. So you cannot use this normal concentration thing, right? Okay, if you are using this general thing, the molality, wait, the molality, yeah. You see this one, okay. Volume percentage, first you will check about volume percentage, then we will go to molality and molarity. So the volume percentage will be at its maximum. Okay, volume percentage will be at its maximum, right? Because what I've taken 10,000 liters. Okay, and here it is just one drop. So that means what it is going to be like, maybe 0.000000001 liter, maybe it can be. And here it is going to be volume of solution, and it is into 100. The amount, okay, this volume percentage is there, right? It is not going to be very high, it is going to be very less. Okay, extremely less. Very less. Okay, so that means it's literally tending towards 0. Okay, it is literally tending towards 0. So you cannot use your volume percentage, or you can neither use molality. Okay, molality I will say, but you just understand that you cannot use molality and you cannot use volume percentage. Okay, or molarity is actually completely based on, wait, not molality, you check molarity itself. Okay, we will check molarity, not molality. Molality is mass. Okay, so molarity, you check molarity. Molarity is also going to be extremely less. Yes, right, you just check. Molarity is going to be very less, because number of moles of solute, okay, chlorine you take, chlorine given amount, what is a number of moles of solute whole divided by volume of solution into this, right? So that means chlorine, it is going to be very negligible, the numerator is going to be very negligible. Okay, so that means, wait, I will give you one amount itself, that is 0.000 not this much, 0.01 gram is there. Okay, so that means you first calculate n. N is equal to what? 1 into, okay, so 0.01 grams, huh? So that means 0.01 into 10 to the power of minus 3 whole divided by, what can I take? I have to take a chlorine, so chlorine is 35.5 into 10 to the power of minus 3. So minus 3 will be cancelled. You'll be getting 1 by 3550. Okay. So this one will be getting us your number of moles, right? Then whole divided by this 10,000 liters you have to write. Okay, this 10,000 liters you have to write. So you write that 10,000 liters itself. Okay, so now you see it is 10,000 only. So now when you check it, okay, when you check it, here it is not just, here it is molality, no, molarity, m. Okay, here it is molarity. So m is equal to 1 by 3550 into 10,000. Okay, here it is 10,000. You just check this value is going to be very less. Very less. Yes, right? This value is going to be very less. You can say this as also negligible. This is also negligible. You are actually dividing 1 by these many times. That means you are separating 1 these many times, which is literally 0 only. You just first divide it with 1000. That you just take here itself will be going 0.001. Yes, right. These many it will be going. Then you check here, it will be just going on. Okay, you have to divide it. So it is going to be very less. That is why what people have done is, what mainly these chemistry people have done is, they have taken this new concept, that is PPT, PBT and PMT. Well, the thing that you have to see is, first you will see, in these many million parts, okay, what they are actually asking is in 1 million part, okay, parts per million. That means in 1 million part of this liter is there, right? In 1,000, okay, actually this is 10,000. This is 10,000 liter of water. Okay, that means you are going to take amongst this amount, you take 1 million. Okay, 1 million part of molecules. Okay, for that 1 million parts of molecule, how many parts of chlorine is there? per million how many parts of chlorine is there. That is what the question is. If in case this denominator value, that means if this solvent is more high, then what people will be doing is they will be going to billion. Okay, from million they will be jumping to billion, because since solvent has got increased, that means you have to also increase in this value. So first is when solvent is little bit less, first you have to take parts per million, then after that you have to take parts per billion, then after that you have to take parts per trillion. Okay, parts per trillion. Okay, so that is what this parts per million, parts per billion, parts per trillion is. Next is molarity. What is molarity? See, molarity and molality are little bit similar in name, but they are different only. Molarity is actually first of all represented with the alphabet of capital M. Okay, whereas molality, okay, molality is represented by the symbol of small m. Okay, and molarity is actually number of moles of solute divided by. Even in the case of molality, the numerator is going to be number of moles only. Only the denominator is going to be changed. In the case of molarity, which is here, it is going to be, the denominator is going to be volume of solution in terms of liter. Okay, volume of solution in terms of liter. But whereas in terms of molality, it is going to be number of moles of solute divided by mass of solvent. It is going to be divided by mass of solvent in kg. Okay, so here you can see that it is number of moles of solute, right? So what is solute? A number of moles of solute is going to be this SI unit is going to be, for the numerator you have to write mole. Okay, and here it is going to be liter inverse. Okay, here it is going to be liter inverse. That means, okay, not by liter inverse, just liter inverse. Okay, so that's it. And one more thing that I have to say is that for these two, no SI unit. No SI unit. Do you think that there is SI unit? Here also mass, here also mass, here also volume, here also volume. So volume will be cancelled, mass will be cancelled. But here it is. Okay, here it will be kg per meter cube. Okay, kg per meter cube. So that means it will be kg by meter cube. So that means you can write it as kg into meter to the power of -3. Okay, here it is going to be mole into liter to the power of -1, which I have written here. Okay, so one more thing that I have to see, that is, you check here, it is volume of solution, right? So molarity, and then you are having molality. Okay, so what is molarity? It is going to be NB, we will be saying NB and NA. You check this. 1 always represents solvent. Also A always represents solvent. Okay, and B or 2 always represents solute. Okay, do you know why? Why do they represent like that? Well, generally this is what the reason that I think, and there isn't any other reasonable explanation. Always they'll be taking like this only. First is that it can be probability, like they have just kept like that. But if what I think is, in every experiment you take, in every case you take, always solvent is the one that is being first taken. For an example, in case of sugar syrup also, first you will be having water only. In that particular vessel where you are doing the project, first what you will be having? You will be having water only, where water is the solvent. Where water is the solvent. So solvent is what taken first. Then after that only you will be taking sugar. Yes, right. Where sugar is the solute, which is taken in second hand. So that means solute is 2, and solvent is 1, solvent is 1. This is what I think personally, what is the reason, but I don't know. Maybe there could be any other reason, but probably this is what the reasonable explanation is. And also they will not ask this in the examination, right? Why will they ask this one? Okay, so NB means what? NB na number of moles of B, where B is the solute. Okay, where B is the solute. Solute only. Do you know something? Remembering that solute is this and solvent is this is a big deal. How I do is, solvent is a bigger word, right? Solvent is a bigger word. So that means the quantity is also big. Okay, the quantity is also big. So the quantity is big will be the thing that will be dissolving. Okay, and here the quantity is less and the word is also small, and that is why it is the thing that is being dissolved. so then saturated super, this we have completed. Coming to this case, okay, where the NB by molarity volume of, okay, volume of solution, okay, in liters. Here what you will be taking as NB1D whole divided by mass of, okay, so mass of A, which is mass of solvent. And NB means number of moles of solute. Okay, see here volume. And see here it is mass. Mass has no relationship with temperature. Yes, right. That means it is fixed. It is fixed. It is constant. You can say anything. Okay. Since this molality will not change. Okay. This will not change. Not change based on temperature. Okay. Temperature will not affect it. Pressure will not affect it. Like this, nothing can affect this molality. That is why this is used high. Okay, this is used in a lot of concentration terms. Okay, in order to find concentration, they will be directly going to molality only rather than molarity, because you can see that it is volume, where volume is inversely proportional to temperature. No, directly proportional to temperature. Yes, right. If temperature is high, then volume will be also high, and also volume is inversely proportional. Inversely proportional to pressure. So you can see that this volume is related to temperature and is also related to pressure. So that means this will be changing based on external properties. So this will be used less only, and this will be used a lot. What will be used? Molality will be used a lot. Okay, so normality, we have formality, we have, see here I've written parts per billion, parts per trillion, and also I've written this. Okay, then here we will be having mole fraction, which is very important. Okay, so coming to normality and formality, well, this is not asked that much, okay, but this is not asked that much, so you cannot give first priority to this, okay, but you have to give first priority to this. Okay, in comparison, you have to give first priority to normality. See, normality is actually gram equivalent weight by volume of the solution. Very similar to molarity. There it is gram molar mass. Okay, that it is not gram molar mass, it is number of solutes. Okay, number of moles of solutes. Here it is gram equivalent weight by volume of the solution. Okay, volume of the solution. And one more thing that I have to say, if in case volume is there now, okay, if in case volume is there in the denominator, then it will be always solution. In the denominator, if volume is there now, then always will be solution only. Okay, if in case it is in the numerator, then only it can be solute, or it can be if in case it is in the numerator, it will be only solute. Okay, it will be only solute. Not only for volume, it is also for mass percentage, volume percentage, mass by volume percentage. It is also for molarity. For parts per million also, you can see that it is mass of. You can see that it is mass of solute divided by mass of solution. And one more thing that I have to say is, see here it is 10 to the power of 6. Okay, here it is just 100. Mass by mass percentage. Okay, that is what the difference is. Only 10 to the power of 4 is what the difference between them. Other than that, nothing is the difference. Okay, so yeah, so gram equivalence weight by volume of solution. So what is gram equivalence weight, by the way? Gram equivalence weight is the number of moles of solute divided by n factor. Okay, so divided by n factor. N factor. What is n factor? Well, it depends upon every compound. Okay, it is not a fixed value, it depends upon every compound. Okay, so it is actually number of ions created. Ions created. It can be either cation or anion. Okay, then you have to take either cation or you can take either anion. For an example, for NaCl you take. Okay, for the case of NaCl you take. Here will be split into Na plus and then here will be Cl minus, right? So what you have to take is here N factor is 1. Okay, here N factor is 1. Then next is number of replaceable or removable hydrogen H plus or OH minus ions. So this is actually in acids and then this is in bases. Okay, this is in acids and then this is in bases. Okay, so in acids you have to check how many replaceable H plus ions are there, and in bases you have to check. For an example, you take HCl, 1 H plus and then you are having Cl minus. And by the way, just don't look at the acid and just don't say that okay, so here only one hydrogen, so I will put N factor as 1. No, there are many acids. Their number of hydrogens is actually something. It will be something. It will be some sort of X value, and their N factor will be also different. Okay, so it is actually based on this N factor is based on the structure. Okay, it is based on the structure of the compound. Okay, structure of the compound. Okay, well, these two are what very important that you have to note. Generally in questions they'll give you this N factor, or if they don't give you, for some compounds they won't give, for some basic compounds they won't give. You will only have to remember for them. Okay, then normality, yeah, just now we have seen normality. Okay, so gram, okay, it is what, one second, yeah, it is actually molar mass. Yeah, gram molecular mass is also okay. I said here number of moles now. Sorry, it is actually molar mass. Here it is molar mass. I said it wrongly. It is molar mass. Okay, here it is molar mass. Then formality. What is formality? Normality, formality. Okay, molarity. How much lity? Next, see, this is actually number of formula units of solute divided by volume of solution. That's it. Just learn the formula. That's it. Okay. There are some relations between normality and then molality. You will check them. Sorry, molarity, normality and molarity. Okay, so one thing I'll also check about formality. Okay, so by the way, formality is number of formula units of solute divided by volume of the solution, which I already said. What is number of formula units of solute? It is just mass of solute divided by formula mass of solute. Okay, what is formula mass of solute? It is just the molecular mass of solute. So this is just basically moles. Okay, this is just basically moles. So if you ask me what is the difference between formality and then normality, okay, formality and normality, they do have some difference, but for now, in order to understand, you can take that they both are same. Okay, but they do have difference, but their definition is same only. Okay, now coming to N factor. Okay, again some more concept we can discuss. Okay, see, first you take HCl. Its N factor value is going to be 1. Then you take H2. Okay, SO4. Its N factor can be 1 or it can be also 2. Then you take, see here the case, you take H2SO4. It can be H plus HSO4. Okay, or it can be plus SO4 2 minus, like this also it can be. So it can be like this, right? So you can see that here 2 hydrogens are there, so that here it is going to be 2. For acids we are talking about, okay? For acids we are talking about like this you can take, then you take CH3COOH. It will be H plus plus CH2COOH minus. Okay, sorry, here from here will not separate. For any organic acid you cannot separate it from here, you have to separate only from here. It's 12 o'clock, my brain is not working because it's midnight, I have to sleep. Okay, so it is going to be CH3COO minus plus H plus, plus H plus. Okay, so here only acid will separate. For any organic acid, this is what the replaceable hydrogen is, this is not the replaceable hydrogen is. Okay, please don't do that mistake. Okay, then after this you can take H3BO3. For this it is going to be H2BO3 BO3 minus plus H plus, where for this, see, first for this N is going to be 1, okay, because only one hydrogen. Here it is also going to be 1. As I said that these are some exceptional cases. Okay, in case of HNO3 it is going to be H plus and NO3 minus, so here N is going to be 1. For acids like this only you have to do. Okay, whereas for bases you take, no, still some cases is there. SO3 you take, then CO2 you take, then SO2 also you take. Okay, first what you have to do is you have to actually hydrolyze it. So you just hydrolyze it. So here it will be H2SO4. Yes, right, SO3 hydrolyzation is H2SO4 only. So this one can be H2SO4 is what? 1 or 2. Okay, so here CO2 can be hydrolyzed, then it then it will be H2CO3. H2CO3 only. So here when you are checking here, it will be CO3 minus 2 plus H2. Sorry, 2H plus. Okay, plus 2H plus. Okay, yeah, correct. So here N is going to be 2. Okay, N factor is going to be 2. Then SO2 is going to be H2SO3. Here the N factor is also going to be 2, 2, 2. Okay, here also it is going to be 2. See, in every case it is 2, but it does not mean that for everything it is 2, but here every case it is 2. Okay. It depends upon the structure. Maybe for everything also it can be 2. Okay, so next is one very easy trick I have brought. That is what? Phosphor oxides. Okay, for all phosphor oxides you can use. Okay, so phosphor oxides. That means what? This means, for an example, H3PO4. Actually, this is not phosphor oxides. For phosphor compounds. Compounds which has oxygen in it. Okay, so H3PO4. So for this, what you have to do is take total number of oxygen. Total number of oxygen minus 1. Okay, so here how many is there? 4 na? 4 number of oxygen na? Minus 1, 3. Okay, then what else you can? For H3PO3 you take here 3 minus 1, 2. H3PO2 you take here 2 minus 1, which is 1. Okay, see, for bases you have to remember, for oxides you have to remember, for acids you have to remember. Okay, then also ions is there, we will also check that. Next is for bases. Okay, so NaOH you will take, then AlOH3 we will take, then BaOH twice we will take. Okay, then MgOH twice we will take, then at last NH3 we will take. Okay, see here only one OH is there, right? So it is going to be Na plus plus OH minus, which is going to be N factor is equal to 1. Here you can take it as Al3 plus plus OH3 minus, which is sorry, not 3 minus, just minus, okay, minus here 3, okay, which is going to be n factor is equal to 3, okay, 3. Here it is Ba2 plus 2OH minus, which is going to be n factor is equal to 2, because you can see what I'm calculating, total number of OH minus only, okay, here 3, so 3, here 2, so 2, so here also it is going to be Mg2 plus 2OH minus, okay, which is going to be n factor is going to be 2. Then for ammonia, actually you can see that ammonia does not even have OH, then how can I say it as a base? By Lewis, okay, Lewis, it is actually a Lewis base. We will explain in coordinate compound, okay, I will explain it in coordinate compounds. Okay, so by Lewis base it is NH3. Actually, this just accepted donator like that concept, very silly concept. Okay, what you have to do is you have to hydrolyze it. Okay, so then it will be NH4 OH, now 1 OH, so n factor is equal to 1. For this directly you can write like that itself. Okay, OH very easily OH will be separated. Okay, because these two are already in a bond. That is why. But H plus is not like that. H plus is very hectic. H plus is not like that. Okay, so for salts, ions. For salts, you have to use ions. Okay, so that means I can take ions are very easy, right? Everyone can do that. But one example I'll give you: Al2SO 4 thrice. Okay, that means what? Actually, this one's charge is this. This one's charge is this. So metal will be always having positive charge, Al3 plus, and SO4 minus 2. This one should be going here. When it goes, it will be minus 2. Here it will be plus 3. Okay, so you can see Al plus 3 and it is SO4 minus 2. Then what is here? Here it is plus 3 and here it is minus 2. Actually, now what you can do is you have to cross multiply this and this. So 3 into 2, just take their magnitude. Just take their magnitude. So it will be 6. So here n factor is equal to 6. See, n factor is 6. It can be also 6. A very large number only. Then for ions, ions just take their charge. That means for Al plus 3, it is going to be 3 as its n factor. For Cl minus, it's going to be 1 as its n factor. For oxygen minus 2, which is n is going to be its 2 is going to be its n factor. Then for In, okay, plus 2 it can be, or plus 3 also it can be, right? So it is going to be n is going to be 2 or 3 as its n factor. Then Na plus you take, okay, Na plus, K plus, Cl minus, already I have written up. Then like this many compounds are there. Then what? Hydrogen plus, then OH, not for OH minus. Br minus, N3 minus, okay, Bn minus 3, Br minus, okay, like this you are having many compounds. And also Mg plus 2, then Ca plus 2, like still having many compounds, okay, many compounds. Okay, so like that, for this all their charges 1 plus 3 3 2 2, because here minus 3 don't put here also minus 3. Okay, here it is 1, here it is 1. That's it. Now all completed. Next is mole fraction. Very important. In our future part of the solution, even we'll be discussing it a lot. Okay, a lot than usual. Number of moles of one component in a solution divided by total number of moles of all the components in the solution. For an example, okay, so you take solute and solvent. Okay, so that means HCl, you take HCl plus H2O. Okay, so actually this is just the ratio between solute or solvent. Okay, solute or solvent to the solution. Okay, to the solution. That means what? Okay, so I have taken what? HCl plus H2O, right? Okay, so mole fraction in sense, first you have to calculate this one's mole. Okay, it will be having some number of mole, right? This will be also some number of mole, right? By the way, mole is equal to given mass. In question even they will be giving a mass, a given mass whole divided by molar mass. molar mass is what? Their compound mass is also. That means for HCl it is 1 plus 35.5. Okay, for H2O it is 18. That means it is actually 2 plus 16, which is 18. Okay, because for hydrogen mass is going to be 1, and along with that you have to have chlorine, which is going to be 35.5. For H2O, here it is going to be 2 plus mass of oxygen is 16, which is equal to 18. Okay, which is equal to 18. And question even they will be giving you a mass. Okay, actually in mole concept, if in case I have time now, then I will try my level best to put a separate video for mole concept, because this is very important. Mole concept is very important. 9th standard, one of the most confusing topic. Okay, I had like no one in this world could have been confused as I was in 9th standard. Till now I have some confusions here and there. I have to first clarify them and then I have to put a video. Okay, come back to here. It's a mole fraction. What is a fraction first of all? Fraction means 1 by 3 and 2 by 3. Okay, then like that. Okay, like this only fraction is. Okay, here when you are taking in case of mole fraction, actually what is this 1? 1 is the numerator. Okay, what is this 3? 3 is the denominator. Okay, so here what you are having is in a compound. Okay, this is what the compound is. Actually now it has got converted into solution. Okay, solution. Yes, right. Now in the numerator you have to calculate. Actually the question is going to be how much moles are there. Okay, this is a solution, right? In the solution, how much moles are there? Okay, what is the mole fraction, or how much moles are there of this H2O? Okay, in the total solution, how much moles of H2O is there with respect to, okay, with respect to HCl. Okay, with respect to HCl, like that you can take. Actually, it is just the ratio. Okay, ratio of H2O, a ratio of H2O by ratio of HCl along with it. By ratio of HCl along with it. So mole fraction in sense, you have to actually in the numerator the desired mole fraction. For an example, if you want the mole fraction of HCl, okay, mole fraction of HCl, then in the numerator you have to put same. Mole fraction is represented by this symbol. Okay, so chi, this is known as chi. Chi. Okay, so HCl na is equal to N of HCl plus N of HCl plus, sorry, here N of HCl by N of HCl plus H2. Okay, H2O. As I said that, since you are calculating the mole fraction of HCl, it is going to be moles, number of moles of HCl divided by number of moles of HCl plus number of moles of H2O. That's it. Okay, and also since here in this compound I have totally added 2 different substances, right? So this is going to be binary. Okay, so binary compound can have 2 different mole fractions. What are they? Mole fraction of HCl and mole fraction of H2O. That's it. Okay, so when you are adding mole fraction of HCl and mole fraction of H2O, that means chi of HCl, okay, is added along with, okay, is added along with chi of H2O. Okay, so this is going to give you 1 as the primary result. Okay, as your result. So that means mole fraction of the total solution to itself is 1. Okay, next here I've got you some other extra formulas, and these formulas are more than enough. And here is the place where I've explained it seems more concept a bit. I mean, I have explained a formula, a sum, I think. Okay. By the way, only one trick to do all the formulas. Convert, if in case mass I've said, wherever I said mass or weight, convert everything in terms of kg. Okay. Put 10 to the power of minus 3 if it is in grams. Okay. Then you do the sums. Everything will be easy. Okay. Here for an example, number of moles you take. Okay. Number of moles you take. They have given. Okay. Now they are asking us to calculate moles of number of moles of. They have given 9 grams. Or 9 grams. Yeah, 9 grams. 9 grams of H2O Okay, then how many moles is there? Very easy, very easy and basic sum. That is why I have taken this. So that means what? First is N of H2O. That means you are actually calculating number of moles of H2O. First, what is given mass? They have given 9 grams, right? So 9 into what is mass? Mass is SI unit is kg. So convert this grams into kg. It is going to be 10 to the power of minus 3 whole divided by total molecular mass. What is molecular mass of H2O? It is going to be 18. So 18 into 10 to the power of minus 3. Okay, because when I'm explaining mole concept, you will understand more better. But I'm not going to go that much deeper in mole concept. Mole concept is where, okay, you are actually here having 18, right? You are having here 18 grams. That is because here there are totally 6.023 into 10 to the power of 23. In some books or in some textbooks, they have given, in place of 2, 3, they have given also 2, 2. Okay, personally, I like to take here 2, 3 because it is actually kind of easy to remember this value when here also 2, 3 and here also 2, 3. When if here it is 2, 2 and here it is 2, 3, little bit of problem arises for me. So that is why 2, 3, 2, 3. And in some textbooks they have given it as 2, 3. In some textbooks they have given it as 2, 2. Okay, so I have taken it as 2, 3 itself. And also it is 0.23 is a very big value. Okay, so come back to here itself. They have given you the molecular weight. Okay, the molecular weight of water is 18 grams. Okay, sorry, 18 AMU. It is because wait 1 second. 18 grams is what the actual weight, okay, of water. That is because this 18 grams of water is there, right? That has 6.023 into 10 to the power of 23 molecules in it. Okay, molecules in it. Okay, so cancel. It is going to be 1 by 2. That is why I have taken it as 18. Okay. Next is coming to here itself. Molar solution, semi-molar solution, decimolar solution, centimolar solution, decamolar solution, millimolar solution. First is molar solution. Molar solution means the molarity is 1. Okay, when the molarity is 1 for a solution, whenever for a solution molarity is 1, we will say it as a molar solution. Whenever for a solution molarity is actually 0.5, okay, then we will say it as semi-molar solution. Okay, for a circle like semicircle we say it, right? Okay, then whenever for a solution its molarity is 0.1, then we will say it as decimolar solution. Okay, correct. Okay. Then whenever for a solution molarity is 0.01, then we will say it as a centimolar solution. Whenever for a solution its molarity is 0.001, we will say it as a millimolar solution. Then whenever for a solution its molarity is 10, we will say it as a decamolar solution. Okay. See here, I have given you some other formulas also. That is, molarity is equal to 10Y by GMM, which is where Y is your mass by volume percentage. Okay, your mass by volume percentage or weight by volume percentage. Okay, Y is that one. Then gram molar mass is GMM. GMM is your gram molar mass. GEM is your gram equivalence mass. Then your D is your density. Your X is mass by mass percentage. Then your, what else do we have? GEM. This is also M and D. Okay, this is also M and D. Well, I'll write them all again. Okay, so check. First is molarity. Okay, for molarity, it is going to be 10 dx whole divided by GMM. Okay, for molarity, it is going to be 10 dx by GMM, where your dx is, okay, where your d and then your x, where d is your density and your x is mass by mass percentage. Okay, then your I've got out of the range. Okay, next is your normality is 10 dx. Okay, 10 dx whole divided by gram equivalence weight. Okay, gram equivalence weight. Yeah, gram equivalence weight, where your GMM is gram molar mass and your GEW is your gram equivalence weight. Then yeah, gram equivalence weight. Did I say you the formula gram equivalence normality gram equivalence weight? Yeah, I said na gram molar mass by or just molar mass by. Okay, so molar mass is equal to molar mass whole divided by n factor. Okay, n factor. Then also remember this, dx is equal to y, where your y is equal to mass by volume percentage. Okay, is equal to your mass by volume percentage. Okay, so that means in this place what you can substitute? In this place and then in this place you can substitute y and you will go, you'll be getting the same answer only. Okay, so I'll just shorten these to write some other formulas also. There are a lot of formulas like this, okay, but I've taken only a few that is required for our portion. And I don't know how many of you guys have seen a NEET paper. Oh God, it was hell hard. I was like, oh, there is no way that I'm going to take even 300 out of 720. How am I going to take? Okay, so y is equal to m by v percentage. Okay, that's okay. This is okay. All okay. Now what are we going to do? We are going to see next another formula. That is, what is that formula? This one completed, that one completed. Okay, so next is molarity is equal to 1000 density, molality, okay, 1000 of molality whole divided by 1000 of density minus 1000 just density into gram molar mass of solute. Solute is B. Okay, solute is B. Solvent is A. Yeah, solvent is A. Solute is B. Okay. All clear. Just this formula can be a little bit hard. Okay, just this formula can be a little bit hard. Other than that, these formulas are very easy. Okay, fine. Solubility. Okay, so what is your solubility? Solubility is actually the maximum amount of solute that can be dissolved in a solvent at a particular temperature. Okay, correct, at a specified temperature. Okay, I've said, okay, the correct amount, the correct definition only. This is what the definition is, where okay, the maximum amount of solute that can be dissolved in a specified amount of solvent at a specific temperature. And wait a second, I have still 3 other formulas here. Okay, other than this, I also have 3 other formulas. If you want, I can also give them, but that is not something commonly asked in our examination, so that is why I'm a little bit hesitating, but it's okay. What's the problem? I'll just give you one more. Okay, that is XB. Okay, this is kind of important, that is why XB is equal to M into okay, so XB is equal to M into GMM of A whole divided by 1000 plus M into GMMA. Okay, Now coming back to here itself, the maximum amount of solute that can be dissolved in a specific amount of solvent is what actually known as specified temperature. Okay. Next is nature of solute, nature of solvent. Yeah. See, this solubility is there, right? This solubility is actually dependent upon. This solubility is actually dependent upon four different things. Okay. Solubility is dependent upon temperature, pressure, nature of the solute. The primary factor that is driving this nature of solute is density, P, and intermolecular bond. Okay, then nature of the solvent. Solvent, same things are what driving here also. Okay, so first of all, temperature. See, these two cases you can segregate into two different types. Okay, first I will say for gases, then we will talk about liquids and solids. Okay, for liquids and solids, same case only. Okay, first you take gas. Okay, so in the case of gas, first is for temperature. See, for gases, solubility, okay, I will write it as S, is directly proportional to temperature. Okay, for solubility only, it is directly proportional to temperature. Inversely proportional. Yeah, inversely proportional. That means whenever temperature is very less, for the cases of gases, the solubility will be very, very high. I will say why. Okay, here also I will use my brain little bit. You take same molecules, you take molecules of water, you take, okay, little bit space only they will be in. Okay, like this only it will be. Okay, whenever your temperature is increased, that means what? So your temperature is has got retarded. Okay, first we will talk about carbonated drinks. Carbonated drinks. So in the beginning, what will be happening is, it will be in normal condition only. Okay, it will be what? It will be normal condition where the temperature, wait, I will say, pressure should be high. Okay, it will not be normal condition. These two conditions alone will be an exception. Temperature should be less. Okay, temperature should be less, and then your pressure should be high. Okay, it means that for this is liquid water, now this is H2O. Okay, CO2 will be given in. CO2 will be given in. Whenever temperature and pressure is high, these two conditions will support the distance between two molecules to be less. Okay, distance between two molecules to be less. Okay, to be less. That means if in case first when they are in normal condition, normal temperature and then normal pressure, this is what their distance is, which is x. Okay, after this it would have got decreased. Okay, in under these two conditions. Okay, under these two conditions, so now this x would have got decreased by d distance. Okay, so this is what their later condition is. For the cases of gases, this is what very often, because when you are dissolving, okay, when you are dissolving CO2 inside gas, okay, sorry, inside water, so now it has got dissolved, right? And if in case same amount of space is there, now CO2 has got filled everywhere. Okay, now we are dissolving. Okay, we are dissolving. If same amount of space remains as such, then this CO2 will start to escape from this bond. Okay, it will start to escape from this bond or between these spaces. It will not stay there because it is gas, right? Gas will always like to move. Okay, because for gases, kinetic energy is always high. Okay, but for liquids, it is little bit higher than solids, and for solids it's very less. Okay, for solids it's very less. That is why we have studied kinetic energy or kinetic theory of gases in class 11th standard, right? Because for gases, kinetic energy is very less. Sorry, is very high. But whereas for solids, it is very low. Okay. Then kinetic theory of gases. That is what we have studied in our class 11th standard. One of the most important things is random motion. Okay, they have this random motion because of their high kinetic energy. Okay. Coming back to this concept itself, they will easily escape because the space between them is not that much. Okay, whenever you are giving lot of pressure now, then in that time these gases will not have any place to go. So they are stuck in there. Literally, you are forcing them to be there itself. Okay, don't move anywhere. So that is why, in order to decrease this distance, what you are doing, you are actually decreasing the temperature and you are increasing the pressure. So that this distance will be decreased and the gases will be remaining inside that liquid itself. Then when we will be getting that sprinting nature inside our mouth. Okay, then that's it. This is what the reason is. Okay, then coming to density, if in case this density of gas is high, okay, density of gas is high, that means solute is very high, you take, that means this gas will not, what is this? This is not gas. That means this gas will not dissolve properly, okay, will not dissolve properly because of its density. Okay, because of its density, it will not dissolve properly. But for the gases which are having less density, okay, it will dissolve properly. Okay, will dissolve properly. Okay, and also if this liquid is having a high density now, if this liquid, that means this solvent is having high density now, that means what? Pressure. Okay, for this pressure is already high. That means it will be easily dissociating. Okay, that means it will be dissociating very high because of its density is high. So that means pressure is already high. All you have to do is you have to decrease the temperature. Okay, all you have to do is you have to decrease the temperature for the case of solvent. Okay, but if in case density is less, if density is very less, then that means gases can easily escape. Yes, right. So you have to increase its density. So in order to increase, only what you are doing, you are increasing its pressure. Okay, what is density? Density is mass by volume, right? That means what? For an example, here, okay, you take water itself. Here, this much is what the mass. Okay, this is what the volume is. Okay, this is what the volume is. And then in this volume, there is some X amount of mass. Okay, some X amount of mass. Density of water is, I think, it is 1. Okay, so that means here it is 1. That means here this is also going to be meter. 1 only. I'll check 1 second. Okay, so in a meter cube there can be 1000 kg of water. Okay, 1000 kg of water, and also approximately density is equal to 997 kg per meter. Okay, for water. Okay, leave that. Okay, so since 1000 kg of mass can be given in 1 meter cube, that means this is also 1 meter, this is also 1 meter, okay, and this is also this side. Okay, the Z axis is also 1 meter. Okay, that means this is also 1 meter. That much is there. Now, if you can stuff still more water there, then what you have to do? You have to compress water, right? So, in order to compress you are actually increasing the pressure and reducing the temperature. Okay, then automatically density will be increased. If density has got increased, then what will happen? Then all the gases will be easily dissolving. Okay, so that is what here I said. Okay, and by the way, for solids, when we are talking, okay, when we are talking about solids, for solids, solubility is directly proportional to temperature for the cases of solids. Okay, and for here only, for gases only, it is like this, and for solids, solubility is inversely proportional to pressure. For solids, it is inversely proportional to pressure. Okay, this you have to remember. And solubility is actually none other than our solvent, mass of solvent divided by mass of solute. Mass of solvent divided by mass of solute. See, mass of solute divided by mass of solvent. Always solute will be in the numerator only. You check. you check. Solute, numerator. Here also you check. Solute, numerator. Here also you can check. It will be also gram equivalence weight of solute only. Okay, so you check here solute, solute, solute. Here also you can check solute. Solute will be always in the numerator. Okay, then yeah, so solute by solvent into 100. Concentration formula is also same, but not 100, will not be there. Now we have entered into a very important thing. This can be asked as 3 mark. Okay, very, very, very important. This can be asked as 3 mark. Okay, but I'm going to erase this. Okay. And also I'm going to erase this. Because I'm going to write and show you all. Okay. You first check here. What is Henry's law? In general, this is water. Okay, this is what? This is water. Okay, so this is water. Normally, in any liquid you take, there will be some amount of gases that will be dissolved. Even in water you take, N2 will be dissolved. Okay, in water N2 will be dissolved, CO2 will be dissolved, O2 will be dissolved, some other gases will be also dissolved in water itself. Okay, so if in case the amount of this water, that means their concentration, okay, this concentration of this gas, not water, concentration of these gases are high. Okay, so concentration of these gases are high, then when you boil this, what will happen? Automatically temperature will increase, right? So this gas will be coming out of this water or this liquid in the form of gaseous state. So that means since concentration is high, automatically that gaseous state or that vapor state will be producing some sort of pressure, right? Yes, right. So that means that vapor pressure is also going to be very high. That pressure of that vapor is also going to be very, very, very high. Okay, that depends upon this concentration only. That is what in English they have written there. Well, I was the one who has written that in here, but it was given by Henry. Okay, it was given by Henry. What Henry says is that the partial pressure of the gas in vapor phase is proportional to the fraction of, it is proportional to the mole fraction of the gas in the solution. Actually, this concentration is there, right? This concentration is directly proportional to mole fraction. So when I was explaining this concept, wherever I said the word mole fraction, wherever I said this word concentration, substitute it with mole fraction. Okay, so the partial pressure of the gas in vapor phase, that means here gas will be there, right? That will be in vapor phase, right? Okay, so that is going to be directly proportional to this mole fraction, because this vapor pressure, if this vapor pressure is very high, okay, because this concentration is very high. Okay, if concentration is very high, then mole fraction is also going to be very high. That means if mole fraction is high now, then automatically your vapor phase of the gas is also going to be very high. I hope you all can get me. By the way, I will also say you the difference. Okay, I will also say you the difference between vapor pressure and partial pressure. Okay, see, first of all, this vapor pressure is there, right? This vapor pressure is something that is created by this vapor. Okay, the pressure that is created by the vapor is what known as vapor pressure. Okay, but this correct only. Okay, but that pressure, okay, this pressure will be created by this vapor, right? That pressure is created on this solution. Okay, that pressure is created on the solution itself. That means when this pressure, that means when this vapor is being created, automatically that vapor will be creating some sort of pressure, and that pressure will be exerted on the solution itself. Okay, and when this vapor pressure is equal to the atmospheric pressure, then in that particular time only, it is set as boiling point. Okay, it is what set as, it is set as the boiling point. It is set as the boiling point. Okay, and when this vapor pressure of this solution, okay, this is of the solution and this is of these, okay, this pressure of this ATM, that is pressure of this atmosphere. Okay, then for the case of freezing, this is for boiling point. Okay, for the case of freezing, vapor pressure of liquid, okay, vapor pressure of liquid, Vp of liquid should be equal to vapor pressure of solid. Okay, vapor pressure of liquid should be equal to the vapor pressure of solid, and yeah, this is for freezing. I think it's raining outside. Okay, anyways, you cannot hear it. Vapor pressure of solution is equal to atmospheric pressure. Now then it is what it is for boiling point. Whenever it is like liquid, for freezing, it is vapor pressure of liquid should be equal to the vapor pressure of solid. Okay, ghost is communicating with me. Okay, it is saying me to have sleep. Now we will go to this concept itself, which is Henry's law, where in case of Henry's law, first is pressure is directly proportional to mole fraction, right? I said this one, and pressure will be equal to a constant, okay, which is said as kH into mole fraction. We can keep it as A. Okay, where that is, this is what the gas, mole fraction of the gas, okay, this is what the mole fraction of the gas. Okay, so here kH is there now. This kH is what said as Henry's law constant. Okay, and this kH, okay, this kH is inversely proportional to the solubility. Okay, then another thing, that is this kH is different, okay, has different values for different temperatures. Okay, it has different values for different temperatures, and then it depends on the nature of the gas. Okay, depends on the nature of the gas. Okay, that's it for that. Then coming to here, see, this is one board examination question. Why aquatic lives can live in cold water easily than hot water? I know that is not a correct English. Anyways, see, aquatic lives can live more comfortable in cold water than hot water, because in cold water what will be their temperature is less. Okay, temperature is less and pressure will be high. That means O2's dissolving nature will be also very high in this water. So that means these marine lives can inhale a lot of oxygen. There will be a lot of availability of oxygen in that water. But whereas in hot water like springs, okay, here temperature is high, so that means pressure will be also high. By the way, pressure and temperature are inversely proportional. Okay, so these two are there, right? So because of this, O2's dissociation will be also very less. Okay, O2 dissociation will be very less. So that means these animals cannot inhale proper oxygen, and their lungs, their body is accommodated and has got evolved in such a way that they don't want that much of oxygen. Okay, but that is not in our chemistry, but this is what you have to write. That means you don't write that evolution at all. Okay, that is not in our portion. Just write that they cannot live comfortable in hot water because of less dissociation of oxygen in the water. That's it. Okay. Next is in real life. Okay, whenever in real life we are getting some problems. Okay, two problems that I have to say. Okay, and one basic, what is that? One basic proving thing. See, first of all, applications of Henry's law is there, right? First, in soda water we are explaining. I've already explained this very clearly in soda water. Bends and anoxia. What is bends and what is anoxia? Have you all done scuba diving? Have you all done trucking? When you are going to scuba diving, actually they will be giving you a suit, okay, and along with that suit they will be giving you two cans which are very heavy, and they will be giving you a pipe like thing that you have to put in your mouth, then goggles that will be given, then for legs they will be giving you fins, then gloves will be there, okay, and it will be fabric. The total cloth will be fabric. This much of protection is required in order to survive that pressure. Well, this is for professional scuba divers. And for some basic scuba diving also, the same suit only, but the texture, the quality all will be lesser than for the professional scuba divers. Here, for scuba divers who are doing this professionally, they will be for doing pearls collection or for researchers, okay, biomarine researchers or they, right? For those persons, what will be actually, they use this method, that is, pressure will be very high, okay, because pressure is very high, then automatically temperature will be a little bit high, in the cold, in the bottommost, okay, so pressure will be very high, right? So because of that, nitrogen will be dissociated in their blood, okay, it would have got dissociated in their blood stream, so that nitrogen will be all over in their blood, okay. When they start to come up, okay, automatically pressure reduces, so that means the dissolved nitrogen in their body will be also reduced. That means they'll all come up, okay, they'll come out of their body, so there will be air ventilations in the bloodstream. That will be causing extreme pain, okay, in awful pain. That is what known as bends, okay. In order to avoid this, what happens, okay, what we do is helium, okay, with 11.7% is used, helium with 11.7%, then oxygen with 32.1%, nitrogen with 56.1%, okay, nitrogen with 56.1%. Next is anoxia. In the extreme places, like in extreme peaks, first this is an extreme bottom, this is an extreme peak, okay, there the amount of oxygen availability will be very less because oxygen is kind of heavier molecule, so they will be available in the ground level only, okay, in the mountain surface at all they won't be that much available. So because of that, the persons who are doing trucking also, they will also take this oxygen tank, but some persons won't, okay. For those persons, what will be happening is they will not be able to think properly, okay, they will not be able to think properly, so that particular condition is what known as anoxia. They will be very weak, okay, they will be having the inability to think. That is why you will be getting yawning, okay, you know, whenever you get yawning, it is not just because of lack of sleep, or it is not just because of sleep, it is also in you will not be having sufficient amount of oxygen, okay. Then, and whatever I said about that scuba diving cloth, that is also not something that is yours supposed to write. Just write what is bends, okay. Then dissolution is an exothermic process. Dissolution is an exothermic process. Please note this. Now we will be coming to our Raoult's law, and we will end this total chapter itself with Raoult's. That means this first video with Raoult's law, because I'm having leg pain. I don't know for how much time I'm taking this video, maybe for 1.5 hours. Yeah, 1 hour 40 minutes. So with this Raoult's law, applications of Raoult's law, we will complete this. Okay, and special type of Raoult's law we will not go. Okay, no, it's special type of Henry's law. Okay. Then in the next video we'll see about ideal, non-ideal, then all those blah blah stories. Okay, first is Raoult's law. What this said is, clone fill with okay, so we will fill this with orange and we will fill this with red and we will fill this with white. Okay, so it's more like when you add white to red you will get orange. Okay, so you are having solute you are having here solute, here you are having solvent, and here you are having the solution. Okay, fine, Packard, and super amazing. I'm even appreciating myself. Self-appreciation is mandatory. Okay. Is it all applicable? Okay, yeah, everything can be seen, but with a blurry thing. Okay, so solute solvents. See, when you boil this solute, okay, I'll take this solute as, what is solute taken? B. Okay, so let it be taken as B only, na? It is taken as B, but we have not mentioned. Okay, I'll take this as solute, na? Okay, so this is B. Solvent, A. Okay. So, solute, when you boil this solute alone, that means you are giving here fire. Okay, here you are giving fire. That means it will be giving you some sort of pressure, right? That pressure is said as P not B. Okay, here when you are giving here pressure, sorry, fire, then automatically that will be giving you some sort of pressure that is going to be P not A. Okay, here actually it is which color? I'll take pink color. Okay, here you are having BB bond. Okay, what is this BB bond? That is, this solute will be having a bond with itself, right? Okay, so what you have to do is you have to break that bond and you have to release this BB, and then this BB will be going out. B will be going out, okay, as gas. Okay, as gas. Here it is in liquid state. Okay, when it is going out, it will be going in. It will be going out as gaseous state only. Okay, it will be going out as gaseous state only. For this, I have to take a light color. Okay. So that pressure, this B, you have to break this bond, and to break that bond only you want some sort of energy. That energy is what? The kinetic energy. Kinetic energy is produced by heat energy. Okay, well you can say that this bond is broken down by heat energy itself. Okay, now next is solvent. Coming to the case of solvent, here it is AA. Okay, here it is AA. In order to break this, and they will be also going out. Okay, here it is AB. Okay, here it is AB. You have to break this, and it will be A, and here it will be B. Here it is A, A. Here it is B, B. Here it is A and B. Okay. Now we take this one. Here it is going to be PA plus PB. Okay, PA plus PB. Now, what is said is, okay, this PA will be high. Okay, this PA will be high. Where is that? One second. Where is that? See, PA and XA. This relationship just now you have seen, right? P and XA you have seen now. So this PA, that means this PA will be greater than XA. It will be directly proportional to XA. Just now we have seen this here. Yes, right? So same thing is applicable here also. Okay, then for PB is directly proportional to XB. Okay, fine. Now, in order to remove this proportionality, here what happens is, here from liquid you are not actually, here what happens is, here you are having a liquid, and for that mole fraction you are taking, okay, accountability. Well, here only one liquid is there, here there is no solute, here there is no solvent, either it can be solute, here either it can be solvent, or even it can be solution. But here it is not like that. Okay, in terms of solute and solvent you want to write. So what you can write? You can write it as, okay, so you have to write it as, in order to remove this proportionality you are not supposed to put KH here, you are supposed to put P naught A into XA. Okay, and here also you are supposed to put PB is equal to P naught B into XB. Okay. And here this total pressure is what? This one. Okay, P net. When you're taking only solvent, then this is what P net. When you're taking only solute, then this is what P net. Okay, so this is what P net, right? Now you write this. Okay. Okay, so P net is equal to PA. What is PA? What is PA? I don't have a PA, but it will be good if I have one. P naught A into XA plus P naught B into XB. Okay, I've got this. Fine, super, amazing, pakka, done. I'm even appreciating myself again. Now, what we know is, I said this already. Okay, where is that mole fraction? Here you are. I said, right, XA plus XB is equal to 1. Okay, so XA plus XB is equal to 1. Now, I don't like this term called, what term I don't like? I don't like this term called A. Okay, I don't like this term called A only I don't like. Okay, so XA is equal to 1 minus XB. Correct? So substitute this here. So then that means it will be P net is equal to P naught A into 1 minus XB plus P naught B into XB. Correct, right? So then that means it will be P net is equal to P naught A plus P naught A into XB plus P naught B into XB, right? Okay, so you can take XB common, or P naught A common. So I'm going to take XB as common. Okay, so that means at last I'm going to get this equation. P net is equal to, or P total, okay, is equal to P naught A plus XB, okay, which is going to be, wait. Minus is going to be there, no? Minus P naught A into XB plus, okay. Now what I'm going to do is I'm going to take it as common. So XB I've taken common, so then it will be P naught B minus P naught A. Okay, so P naught B minus, okay, correct. This is your formula. P net is equal to P naught A plus XB into P naught B minus P naught A. How are you going to remember this? That is what even I'm wondering. Maybe you just remember this one formula. Okay, this one formula remembering isn't that such a big deal. Okay, you just remember this one formula. Now, go to your examination hall. Then if there is a question based on this Raoult's law, then you first write this one. Okay, if they have given you only XA, okay, if they have given you only XA, then write everything in terms of XA. Convert XB also in terms of XA. If they have given you only XB, then convert XA also in terms of XB. Then you substitute this formula, then you will be getting it. Okay, so you just remember this one formula, then do the same application which I have done. Okay. You check here, there are some common points, right? Raoult's law and then Henry's law. Okay, Raoult's law and then Henry's law. Relationship between Raoult's law. Raoult's law. Oh, I forgot the spelling, but I explained the concept. How great am I? R-A-O-U-L, Raoult's law. and Henry's law. Okay, I said some concept. Okay, I said some similarities, right? What is that? PA is equal to P naught A into XA. Then PA is equal to KH into XA, right? Okay, equal now. Now equate these two. Then it will be what? KH is equal to P naught A. So this says that. This says what? This says that Raoult's law spelling. Raoult's law is a special case. Of Henry's law. Actually, while writing here also, I thought of saying that you can write here KH also, or you can write here P naught A also. But many people will be confused. Then what is the difference? Actually, these are same only. This is just a special case of this one. That's what. Okay, that is what the difference. They are literally same only. Raoult's law and then Henry's law are literally same only. It is just a special case. Okay, it is what? It is just a special case. Then last concept, I will complete this with that last concept, and this is what Raoult's law's definition is. Next, in this next thing, we will start with ideal, non-ideal. Then we will go with colligative properties. Okay, then we will go with colligative properties. Okay, so this Raoult's law is there, right? This is actually vapor pressure of a solution is related to the vapor pressure of each component and their mole fraction in the solution. So vapor pressure of a solution, you can see that the total vapor pressure of a solution is related to the each vapor pressure, this vapor pressure and then this vapor pressure. Okay, this vapor pressure and this vapor pressure, and along with their so the total net vapor pressure of a solution is related to its vapor pressure of its constituents along with its mole fraction. Okay, along with its mole fraction. That is what it has said. Okay, then after completion of this, special case in Raoult's law. Okay, Raoult's law itself is a special case of Henry's law. In that we are seeing another special case. Okay, application you can take. Okay, an application. Now, P net is equal to P naught A XA plus P naught B XB. Okay, this is what we have seen. Here, P net is equal to. Now, what I'm actually doing is, this B is what? This B is what? The solute. What solute? Okay, solute. Now, when I add solute is volatile. Okay, when I say solute is non-volatile. Okay, whenever the solute is non-volatile, or also this can be solid. Okay, solid or non-volatile, both mean same only here. Okay, solid. Then that means. Okay, so P naught B will not be there. What is non-volatile? That means it cannot be converted into a gaseous state. Liquid will remain liquid only no matter how much temperature you have given. So that means P naught B is equal to 0. Okay, P naught B is equal to 0 because it will not create any pressure at all. Okay, so that means I can equate this total term to 0. This to 0. Okay, so the remaining terminologies will be P net is equal to P naught A into XA, right? Okay, so I can write here XA. Okay, here XA is equal to 1 minus XB. So P net is equal to P naught A into 1 minus XB. So we have P naught A minus P naught A into XB. So you have got this. That's it. Pakka done. Super amazing. Fine. Okay. So then ideal also shall be complete. No, I don't have that much of energy to stand actually. And still I have to, well, I'm saying ideal or not, just like that I'll say I have to erase this total thing and then I have to again start it fresh, because ideal and non-ideal is such an important topic. But I can start next video freshly with colligative properties and then abnormal mass. Also taken notes. Okay, so that means that's it for today's video, and tomorrow we will be dealing with some other concepts. Okay, so thank you, bye bye.